Yes, dear friends, in this video I will tell you some question based on Lenz law. Lenz law. And I told you Lenz law is the basic law to find the direction of induced current or induced EMF. And Lenz law states that the direction of induced current is such that it opposes the cause by virtue of which it is produced. You know? In some books, you are told right hand screw rule, right hand thumb rule. That is not a general rule. Lenz law is basic law to find the direction of induced current. Now see here in this figure 1. Figure 1, 2, 3, 4. In figure 1, the north pole, south pole magnet is there and magnet is going away with some speed. Then what is the direction of induced current in wire PQ? What is the direction of induced current in wire PQ? So as north pole going away and motion, so due to the change of flux, actually magnetic is due this way. So that while moving the magnet away from this, the flux is decreasing. Flux is decreasing and therefore the induced currents should be such that it should maintain same flux, magnetic flux, and that is only if the induced current here produce magnetic field in the same direction. The magnetic field of this bar magnet here is from right to left. As it is moving away, the magnetic field is still decreasing inside the solenoid, due to which flux will be changing, and that changing flux produce induced EMF due to which current flows. So it has to produce here current in such a manner that flux will increase. From right hand palm rule for solenoid we can use this. Okay, if this is the solenoid here, if we hold in right hand in such a way that curl of finger is along the direction of looping, then thumb stretch along solenoid will give direction of induced magnetic field. Other way, north pole going away, so its motion should be opposed, and there should be south pole here. If south pole current should be clockwise. So here current will be flowing like this. And hence, but you are asked current in, this is the induced current here. Induced current due to motion of magnet going away. So here it will flow from P to Q. Generally they ask here, what is the direction of current in this? I think it is very clear. Lenz law states that direction of induced current says that it opposes the cause by virtue of which it is produced. So here magnet moving away, one region के magnet moving away, so its motion should be opposed, so there should be south pole. Secondly, when magnet moving away, magnetic field here inside the coil will decrease because farther the point from magnet, the weaker the field. So it will try, the induced current will produce field in same direction, and it is possible only if current flows here anti-clockwise. Is the anti-clockwise flow. Here should be south pole, north pole. So induced current in wire conductor resistance R will flow from P to Q. I think so. Here you can't apply right hand thumb rule. I have book here with me. They have been right hand rule. Lenz law is basic law. Now people are improving. They are applying this thing. Now there are two solenoid again. One has no battery connected across it, but conductor CD is there. R conductor. So here, this is the rheostat, and this is moved this way. The current here is flowing like this. So first of all, we have to decide what is the direction of magnetic field of this. Again, it is, so is the field of this magnet this way, and here also this way. It will be south pole, it will be north pole. Going this way. We have to hold this. Now, if we are moving this rheostat this way, means we are decreasing the resistance, so current will be increasing here. That increase of current will be increased field in this direction, so it should produce current induced will be there, so that field should not increase, and that is only possible if current flows this way here. Because now the field will be like this, and by field of this solenoid here is right to left. And because when we are changing the position of rheostat this way automatically, we are decreasing resistance, and hence current will be increasing this, and this increasing current will increase the magnetic field here. So induced current will keep the magnetic same, so induced field should be this way, B dash, and it is only possible current flow this way. So here current will from D to C, D to C. Go here this way, so it will go this way. So this is the application of Lenz law here. Now, in this figure here, again there are two solenoids. Here current was there, the key was pressed. So when key, this is pressing key, when we release the key, what direction of induced current here? Actually, when current is passing through this, the field again due to this solenoid will be pointing from this direction, right to left. So magnetic field here this way, due to this solenoid. Due to solenoid which carries current I here, the field in this solenoid is again from right to left. As we made it free, the current here start decreasing. Current in this coil decreasing, so magnetic field will decrease again. So it will produce magnetic field in the same direction. It is only possible if this carries current this way. We hold like this, not like this. So then here current will come like this. So again here y to x. So we can apply Lenz law to find the direction of induced current. Here it is a conducting loop placed horizontally. A conductor is normal to this plane. The loop is this. Current is going up through this conducting wire. So if I is increasing here, in this conductor current is increasing, then what direction of induced current in this circular loop? This conductor carrying current I is normal to plane of loop and outward, like this. है ना, ये ऐसे पास हो रहा है इसमें से. तो कंडक्टर carrying current upward. So what is the direction of induced current in this loop? If current I is increasing, you know, if this is a conductor here, the field line will be in horizontal plane, and the plane of this loop is also horizontal. So no magnetic flux get linked with this. इसके साथ कोई magnetic flux link नहीं होगा, इसलिए whether current increase or decrease, no induced current here. No induced current. No induced current. So these are some questions. Why not? Because no field lines of this are in this plane. They are not passing. Flux will get increased only when field line pass through the area. Now I come to some more questions. A question has been asked 2 times in entrance test 4 in AIEEE, and once it was in IIT. Initially IIT different IIT and different engineering college were giving test differently. So here a very good question there. Here the magnetic field, it exists everywhere, no end. There is no end. This field is existing up to large distance. Here in this field, there is a conducting loop. It is moving like this. A, B, C, D, the conducting loop moving with velocity v in this field. Moving in this field. So you are asked there, what is the magnitude? Will there be EM induced and induced current? Will there be induced current in the loop and induced EM is there? This loop here in the field, remain in the field, but move here. So will there be an induced EMF or induced current? What you say? Actually, you are not with me here, so I can't check your expression or your feeling. What you say? It appears that there is no change of flux. Till the loop conduct rectangular or circular कैसी भी हो, it is there. Flux does not change. So it appears that no induced EMF there. But if you see, I told you third law कि whenever a magnetic flux linked with the coil changes or a conductor whose magnetic field cutting the field lines, EMF is there, induced EMF. Here these two sides are cutting the field line. The magnetic field is normal to plain paper or board and it is in this move. So side AB and CD are cutting the field line. And therefore, modulus is equal to BN. There will be potential difference across this that has same value. Potential at B, potential at A, potential at C and D होगा. So point potential at B and C same, and A and D same. And current flow due to potential difference. So induced EMF is there. Induced EMF is there. But induced current is zero. No current will flow because B and B same है दोनों के लिए.